Many people believe that focus is simply forcing yourself to stare at something for hours. But that's as ineffective as trying to push a wall with your bare hands. Here's the secret. Energy must be channeled, not wasted. Just like light, when concentrated into a laser beam, gains the power to cut through steel, your attention, when directed with relentless precision, has the power to break through any barrier in life. Pay close attention to me, because this can change the way you see yourself. Your brain works like a particle accelerator. Billions of electrical signals are firing every second, colliding, crashing, creating new connections. But without direction, all of that activity is chaotic, scattered, without results. When you learn to create focus tracks, the same way physicists guide beams of particles in straight lines with magnetic fields, what was once confusion turns into organized power. This is the first secret to training your brain like a genius. It's not about thinking of everything. It's about thinking of one thing with such intensity that the world around you disappears. And here is where discipline comes in. Don't confuse discipline with suffering. Discipline is in fact the art of simplification. If you can't explain something in a simple way, it means you haven't understood it. The same applies to your life. If what you're doing feels too complicated, it's because you haven't yet found the clarity that generates true focus. So here's the first exercise I want you to do. Choose one goal, just one, and write it down in a single sentence. Simple, clear, and direct. If you can't summarize it, then you don't yet understand what you truly want. Now, take a deep breath and reflect. How many years have you lost trying to embrace everything, when in reality the secret was to reduce? Think of Newton. Think of Einstein. Geniuses who dedicated decades to just a handful of questions, and because of that, they achieved greatness. Your focus is your most powerful weapon. Use it like a laser beam. Your brain is like a telescope. If you point it at nothing, you'll see only darkness, but if you adjust the lens and choose a single star, suddenly the entire universe begins to reveal itself. Focus is exactly that, the ability to eliminate the noise so you can see what truly matters. But here's the real question. How do you develop greater focus? Pay attention, because here's the truth almost no one dares to say. Focus is not something you find, it's something you train, exactly like a muscle. No one is born with unshakable discipline, but anyone can build it. Think of the physicist who spends hours adjusting an experiment. Every tiny adjustment is a victory against distraction. The same applies to you. Want more focus? Create environments where distraction has no place. Remove the excess. Eliminate notifications. Write down exactly what you'll do in the next hour and do only that. Does it sound simple? It is simple, but that's precisely why it works. If you can't create an environment that favors focus, then you don't yet understand your own mind. Training focus is training your mind to choose, and every choice is an act of power. Don't fool yourself. Every time you give in to distraction, you're strengthening the muscle of weakness. Every time you say no to an interruption, you're strengthening the muscle of focus. And here's a practical exercise for you. Every single day, set aside 30 minutes to concentrate on just one task without interruptions. If your mind starts to wander, bring it back, no matter how many times it happens. This is exactly like training physical endurance. At first, it hurts, but then you realize that pain transforms into strength. In just a few weeks, you'll have developed the ability to dive deeply into anything you choose. Remember this: the brain is plastic. It molds itself according to how you use it. If you feed it distraction, it becomes scattered. If you feed it focus, it sharpens like a blade. The choice is in your hands. And now let me tell you something that might sting a little. If you quit just because someone laughed at you, it means you haven't yet understood what inner strength really is. If you stop because you feel tired, it means you still haven't realized that the body can always go further when the mind commands. Focus doesn't grow in times of comfort. It's born when you face pain, sacrifice, and still choose to keep going. That's how steel is made, through fire. Here's a powerful habit for you. Before going to sleep, write down in a notebook, what did I do today that brought me closer to my goal? What distracted me? What could I have done better? This simple act, repeated every day, creates a vigilant mind. It's like a scientist reviewing every detail of an experiment until nothing escapes. Do this for just a few weeks and you will no longer be the same person. The regret of not having lived up to your potential is infinitely heavier than the pain of discipline. The pain of waking up early, of studying when you don't feel like it, of pushing forward when nobody believes in you. That pain is temporary, but the regret of not giving your all is eternal. So make a pact with yourself now. Train your mind like a genius. Become unbreakable. Now imagine this. You're facing a difficult problem, one of those that feels impossible. Most people give up because they see the challenge as torture. But a genius looks at that same problem as if it were a game. That's exactly how great minds transform physics into something fascinating. Physicists don't study out of obligation. They play with concepts. They sketch. They create funny metaphors. And that's why they're able to go so deep. And here lies one of the greatest secrets of humanity about learning. When you enjoy what you study, you don't just learn more. You also train focus and discipline to levels that seem almost superhuman. So what's the difference between someone who quits quickly and someone who dives deep into an idea until they master it? The difference lies in emotion. The one who finds joy in the process doesn't need external motivation, because the very act of studying, practicing, or creating becomes its own reward. This is the key you need to understand. Focus is not sustained by brute force, but by fascination. Want to improve your focus and discipline? Transform every task into an experiment. Ask yourself, how can I make this more interesting? How can I see this problem from a new perspective? By doing this, you activate curiosity, and curiosity is like a magnet for the mind. It pulls your attention without effort. The first rule is not to fool yourself, and you are the easiest person to fool. That means you can't trick yourself into believing you have focus if you secretly hate the process. The brain rejects what doesn't make sense to it, but when you connect emotionally with what you're doing, focus arises naturally. And every time you practice this kind of playful, creative study, your discipline grows without you even noticing, because discipline stops being a prison and becomes freedom. Discipline is not just about enduring pain. True discipline is being so deeply involved in what you do, so passionate about it, that continuing becomes the most natural path. That is how you create not only unshakable focus, but a mind that learns and expands every single day. And this, right now, could be the moment when you decide to change everything. Your mind is your greatest weapon. It's not external resources, it's not luck, it's not what others say. It's your ability to train your brain like a genius, to develop relentless focus, to build discipline even when no one else believes in you. That is what will define how far you can go. Stay with me here, because you need to understand this. The world is already full of ordinary people, distracted, trapped in empty routines. But those who decide to master their focus, those who cultivate discipline and curiosity, they become unstoppable. They don't play by the rules, they create the rules. They don't wait for opportunities, they build them. So here's the question. Will you keep being just another face in the crowd? Or will you take command of your mind and transform your life into something extraordinary? Be honest with yourself. How many times have you promised to change, only to give up at the first difficulty? How many times have you let distraction win? That ends today. Make a pact right now. Sacrifice what you must, but never sacrifice your future. Train your brain. Sharpen your mind, and success will simply become an inevitable consequence. And I want you to do something right now. Write in the comments, I am unstoppable, to seal this commitment with yourself. This isn't just a phrase, it's an act of decision. Click subscribe, turn on the notification bell, and hit the like button, because this is only the beginning of a journey that can completely transform your life. This is the moment when you stop living as a spectator and start acting as the protagonist. Remember this. Regret weighs forever, but discipline shapes champion. In your hands lies the power to write a new story. So stand up, take action, and prove to the world and to yourself that your focus is truly unstoppable.
We traveled back in time, excited. We thought we had done well. Look at our technology, look at our data, look at our confidence. He wasn't impressed. He was angry, not loud anger, the dangerous kind, the kind that comes from disappointment. He looked at our books, our lectures, our confident explanations, and he stopped us immediately. You don't understand, he said. You've learned to talk about it. That hurt. It was supposed to. We showed formulas. He asked simple questions, not advanced ones, basic ones. Why does it work? What does it actually mean? What would happen if it didn't? Silence. We knew the steps. We didn't know the reason. Somewhere along the way, we replaced curiosity with credentials. We replaced doubt with confidence. We replaced thinking with repetition. And worst of all, we stopped admitting when we didn't know. That's when learning died. He reminded us of something brutal. If you can't explain an idea simply, you don't understand it deeply. And if you don't understand it deeply, you have no right to be certain. Nature doesn't care how elegant your theory sounds. It doesn't care who approved it. It only cares whether it's right. Reality is cruel that way and honest. He wasn't angry because we were wrong. He was angry because we were comfortable being shallow, because we taught answers without questions, because we trained people to pass exams, not to think, because we forgot that the joy of discovery comes from confusion first. Understanding is hard, that's the point. If learning feels easy all the time, you're probably not learning. You're just memorizing. Before we left, he said one last thing. Never fool yourself, and remember, you are the easiest person to fool. That's why he was angry, and that's why we should be too. If you want, next weekend, confusion is the enemy of understanding, but not the honest kind. The real enemy is the confusion we pretend isn't there, the fog we decorate with big words and call knowledge. The moment we stop saying, I don't know, learning doesn't slow down. It stops completely. From that moment on, we're not discovering anything. We're just repeating noises that sound intelligent. People think the opposite of understanding is ignorance. That's wrong. Ignorance is clean. Ignorance knows it doesn't know. Confusion that thinks it understands is poison. It creates confidence without clarity, certainty without truth. And once that happens, curiosity dies. Why ask questions when you believe you already have the answers? Look closely at how we learn things. We memorize definitions. We memorize formulas. We memorize steps. Then we mistake recognition for comprehension. We hear familiar words and feel smart. But ask one simple question, why does this work? And suddenly the room goes quiet. That silence is not a failure of memory. It's a failure of understanding. We've trained ourselves to survive systems, not to understand reality. Exams reward recall, not insight. Presentations reward polish, not depth. The result is a generation that can recite explanations but can't reason through problems. They know the vocabulary of ideas without touching the ideas themselves. And here's the uncomfortable truth. Most of what we confidently explain, we don't actually understand. We've learned to move symbols around without knowing what they represent. We manipulate equations like rituals, hoping the answer appears at the end. When it does, we celebrate. When it doesn't, we blame the math, not our thinking. Real understanding is slow, it's frustrating, it feels stupid before it feels smart. You get lost, you contradict yourself, you ask questions that sound childish, and that's exactly how you know you're doing it right. Understanding begins the moment you're willing to sit inside confusion instead of escaping it with memorized answers. But we hate that discomfort, so we hide it. We cover confusion with authority. We say, that's just how it is, or trust the theory, or experts agree. Sometimes experts are right, sometimes they're wrong, but even when they're right, borrowed certainty is not understanding. It's obedience. Nature doesn't care what you believe. It doesn't care how confident you sound or how many people agree with you. Reality has no respect for reputation. It only responds to what is actually true. You can fool your audience, you can fool your students, you can fool yourself, but you can't fool nature. That's why pretending to understand is so dangerous. It blocks progress, it freezes curiosity. Once you believe you understand something, you stop testing it. You stop poking at it. You stop asking what would happen if one assumption were wrong. And every major breakthrough in history came from someone doing exactly that, questioning what everyone else had stopped questioning. True understanding is not about having answers. It's about knowing which questions matter. It's about being able to explain an idea in plain language, not because simplicity is fashionable, but because clarity is a test of truth. If an idea only works when wrapped in complexity, there's a good chance it doesn't work at all. And here's the part people don't like to hear. Confusion is not something to eliminate quickly. It's something to respect. Confusion is a signal. It's reality telling you that your current model is incomplete. Ignore that signal and you build castles on sand. Listen to it and you rebuild your thinking from the ground up. This is why intellectual honesty matters more than intelligence. Smart people can be confidently wrong. Honest thinkers can be temporarily confused and eventually right. Progress belongs to the second group, not the first. The discipline is brutal but simple. Never confuse familiarity with understanding. Never hide behind jargon. Never accept an explanation you can't explain yourself. And most importantly, never be embarrassed to say, I don't know yet, because I don't know is not weakness. It's the doorway. It's the starting point of every real idea that ever changed how we see the world. Confusion isn't the enemy when you face it. It becomes the enemy only when you pretend it isn't there. We mistook memorization for knowledge, and the mistake was so convenient that we built entire systems around it. Memorization is fast, it's measurable, it looks like progress. You can test it, grade it, certify it, and move on. Real knowledge is none of those things. It's slow, uncomfortable, and difficult to standardize. So we chose the easier substitute and told ourselves it was the real thing. Memorization gives the illusion of competence. You recognize the formula, the definition, the historical date, and your brain signals success. Familiarity feels like understanding, even when it isn't. You can repeat the words, but if the situation changes slightly, if the problem is framed differently, or the assumptions shift, the knowledge collapses instantly. That collapse reveals the truth. Nothing was understood, only stored. Knowledge is not the ability to recall information on demand. Knowledge is the ability to reason when memory fails. It shows itself when you're forced to think without a script, when there's no checklist to follow and no example to copy. If removing the notes removes your understanding, you never had understanding to begin with. We train people to pass tests, not to think. We rewarded speed over depth, certainty over curiosity. The student who asked too many questions slowed the class down. The one who repeated the answer efficiently was praised. Over time, the lesson became clear. Don't explore, perform, don't wonder, deliver. This is how intelligent people become fragile thinkers. They know a lot, but only inside familiar boundaries. The moment a problem refuses to fit the template, panic sets in. They search their memory harder instead of questioning their assumptions. But memory cannot save you when the situation is new. Only understanding can. Memorization is brittle. It breaks under pressure. Knowledge bends and adapts. When you understand something, you can rebuild it from scratch. You can derive it. You can explain why it must be that way and not some other way. When you've only memorized, all you can do is hope the question looks familiar. And here's the uncomfortable part. Most systems don't care. Memorization is efficient. It scales. It produces impressive short-term results. But long-term, it creates thinkers who are afraid to be wrong. Because when your value is tied to recall, admitting uncertainty feels like failure. So people defend weak ideas instead of questioning them. Real knowledge invites doubt. It survives it. In fact, it depends on it. Understanding grows when you stress test ideas, when you push them into uncomfortable territory and see what breaks. Memorization avoids this at all costs. It preserves answers by never challenging them. There's a reason people cling to memorized explanations. They're safe. They come pre-approved. They carry authority. You don't have to take responsibility for them. If they fail, you can say, that's what I was taught. Understanding doesn't give you that escape. When you understand something, you own it. And ownership is risky. But that risk is where thinking begins. Knowledge is not something you store, it's something you can use. It shows up when you can predict outcomes, not just describe past ones. When you can spot nonsense, even when it's wrapped in impressive language. When you can simplify without losing truth. The tragedy is not that memorization exists. It has its place. The tragedy is that we stopped demanding more. We stopped asking students to explain ideas in their own words. We stopped valuing slow, careful reasoning. We stopped rewarding the struggle that precedes real insight. The cost is everywhere. People argue confidently about things they don't understand. They defend positions they can't justify. They confuse agreement with truth and repetition with evidence. All of it traces back to the same error, mistaking recall for comprehension. If you want to know whether you truly understand something, remove the script. Change the context. Ask what-if questions. Try to teach it without using the original words. If the idea survives, you've learned something real. If it collapses, don't be embarrassed. That collapse is the beginning of knowledge, not the end. Memorization feels like progress. Understanding is progress. One fills your head, the other changes how you think. Math became decoration instead of meaning the moment symbols started, impressing us more than understanding. Equations turned into ornaments, something to display, not something to think with. Lines of symbols were treated like proof of intelligence, even when no one could explain what they actually described. The math looked right, sounded sophisticated, and that was enough. Or so we told ourselves. At its core, math is not a performance. It's a language for describing reality with precision. Every symbol stands for an idea, every operation for a relationship. When those ideas are lost, the symbols become empty. You can move them around, manipulate them, and still have no idea what you're saying. That's not mathematics, it's ritual. Somewhere along the way, we started teaching procedures without meaning. Do this step, then that step, and you'll get the correct answer. Why those steps work was considered optional, sometimes even inconvenient. Understanding slowed things down. Efficiency mattered more. And slowly, math stopped being a way to see the world clearly and became a way to survive exams. This creates a dangerous illusion. People who can manipulate symbols fluently are assumed to understand what they represent. But fluency is not comprehension. You can recite a sentence in a foreign language without knowing what it means. Mathematical symbols are no different. Without intuition, they're just shapes on a page. When math becomes decoration, it gains authority without accountability. Complex equations intimidate people into silence. If something is expressed mathematically, it must be true, right? Not necessarily. Math can hide nonsense just as effectively as it can reveal truth. In fact, it's better at hiding nonsense because it looks precise even when the assumptions underneath are rotten. Real mathematical understanding is grounded in physical intuition, logical structure, and clear definitions. You should be able to say what each term means, what would happen if it changed, and why it must be there. If you can't explain what an equation is about, then solving it is meaningless. You're solving puzzles, not problems. This obsession with form over meaning disconnects math from reality. Students learn techniques but never learn how to model the world. They can differentiate and integrate but can't explain what's changing or why accumulation matters. They can solve differential equations yet have no sense of the behavior those equations describe. The map has replaced the territory. And when math loses contact with reality, it becomes fragile. The moment conditions change, the method fails. People don't know how to adapt because they never understood the structure in the first place. They learned the dance, not the music. There's also a psychological cost. When math is taught as decoration, people conclude they're bad at math. What they really mean is they're bad at memorizing rituals without meaning. Anyone would struggle under that system. Understanding is empowering. Memorization is alienating. Math was never meant to be mystical. It was meant to be clear. It's supposed to reduce confusion, not create it. The beauty of mathematics comes from insight, seeing why something must be true, not just that it is. When you strip away meaning, you also strip away beauty. The solution isn't to simplify math into something shallow, it's to reconnect symbols to ideas, to ask constantly, what does this represent? What assumption am I making? What would break if this term disappeared? Those questions turn decoration back into meaning. Math earns its power when it explains something you couldn't see before, when it predicts behavior, when it exposes hidden relationships. Without that, it's just impressive handwriting. Symbols should serve understanding, not replace it. When math stops meaning something, it stops being math at all. Authority replaced curiosity the moment we started as king who said it instead of why it's true. The shift was subtle at first, almost reasonable. Experts exist for a reason. Experience matters. Knowledge accumulates, but somewhere along the way, respect for expertise quietly mutated into obedience, and curiosity, the engine of understanding, was pushed aside as inefficient, even dangerous. Curiosity is slow. It asks uncomfortable questions. It challenges settled ideas. Authority, on the other hand, is convenient. It gives answers without demanding effort. When an authority speaks, thinking feels optional. You can stop exploring and start accepting. That trade-off feels harmless until you realize what it costs. The ability to tell the difference between truth and confidence. The problem isn't authority itself. The problem is unexamined authority. When ideas are accepted because of their source rather than their substance, thinking becomes passive. People learn conclusions without learning the reasoning that produced them. And once the reasoning is gone, the conclusion becomes fragile. defended, not understood. This is how dogma is born. Not from malice, but from comfort. Questioning takes energy. It risks embarrassment. It can make you look ignorant or disrespectful. So people learn to stay quiet. They learn that repeating the accepted answer is safer than asking an honest question. Over time, the questions stop forming altogether. When curiosity disappears, progress slows to a crawl. New ideas don't come from obedience. They come from people who notice cracks in explanations and refuse to ignore them. Every major leap forward began as a question that authority couldn't answer or didn't like being asked. Authority also has a dangerous side effect. It shifts responsibility. If an idea comes from someone powerful, criticizing it feels risky. If it fails, blame is diffused. That's what the experts said. But understanding doesn't outsource responsibility. When you understand something, you're accountable for it. You can defend it, modify it, or abandon it based on evidence. Authority offers no such flexibility. There's another cost we rarely talk about. When authority replaces curiosity, learning becomes hierarchical instead of exploratory. Knowledge flows downward, not outward. Students wait to be told what matters instead of discovering it. They learn to optimize for approval rather than truth. The goal becomes agreement, not understanding. This environment rewards confidence over clarity. The person who speaks decisively, even without depth, is trusted more than the one who hesitates thoughtfully. Curiosity often sounds like uncertainty, and uncertainty is mistaken for weakness. But uncertainty is where real thinking lives. Certainty without examination is just a loud guess. Nature doesn't recognize authority. Reality doesn't check credentials. It responds only to what actually works. You can cite the most respected source in the world, but if the idea doesn't match reality, it will fail, quiet, lie, or catastrophically. Curiosity is what keeps us aligned with reality. It forces constant testing, constant adjustment. The tragedy is that curiosity is natural. Children are relentless questioners. They don't care who said something, they want to know how it works. Authority teaches them to stop. It teaches them that some questions are inappropriate, some ideas are settled, some lines shouldn't be crossed. And in doing so, it trains compliance, not intelligence. Respect for expertise should sharpen curiosity, not replace it. True understanding demands both, learning from those who know more while never surrendering the right to ask why. The moment you're forbidden from questioning, you're no longer learning, you're being managed. Curiosity is not rebellion for its own sake. It's loyalty to truth over comfort. Authority that cannot tolerate curiosity is not protecting knowledge, it's protecting itself. When authority replaces curiosity, thinking becomes fragile. When curiosity challenges authority, understanding grows stronger. Reality doesn't care about our theories, and that's the most uncomfortable truth the thinking mind has to accept. It doesn't care how elegant the model is, how famous the person who proposed it was, or how many people believe it. Reality has no interest in our explanations. It only responds to what actually happens. You can argue with people. You can't argue with nature. Theories are tools, not truths. They are guesses, sometimes brilliant, sometimes less crude, about how the world behaves. When they work, we keep them. When they fail, reality doesn't negotiate. It doesn't offer partial credit for effort or intent. It simply exposes the gap between what we thought and what is. The danger begins when we forget this. When a theory starts to feel sacred, questioning it feels like betrayal. People defend it, patch it, reinterpret failures instead of confronting them. But every time we protect a theory from reality, we weaken our understanding. We trade accuracy for comfort. Reality is ruthless but fair. It applies the same rules to everyone, everywhere, every time. If a bridge collapses, it doesn't matter how confident the engineer was. If a prediction fails, it doesn't matter how respected the theory is. Nature keeps the score, and it never lies. This is why prediction matters more than explanation. Anyone can explain the past after it's happened. Real understanding shows up when you can say what will happen next and be right. A theory that cannot risk being wrong is not a theory, it's a story. Our attachment to theories is emotional, not logical. We invest time, identity, and reputation into them. Admitting they're wrong feels like admitting personal failure. So we rationalize. We add exceptions. We adjust definitions. We protect the idea instead of testing it. Reality doesn't care. It keeps producing results that don't match. Progress happens only when we let theories die. Not because they were stupid, but because they incomplete. Every useful theory is a temporary one. The moment you believe your current explanation is final, you've stopped learning. This is also why authority and consensus can be dangerous when they replace evidence. 1,000 people agreeing on a wrong idea doesn't make it less wrong. Reality doesn't count votes. It doesn't reward popularity, it rewards alignment. Theories should make you humble. They are approximations, lenses through which we see part of the truth. Confusing the lens for reality itself is how errors persist. When observations don't fit, the lens must change, not the world. There's a strange freedom in this. If reality doesn't care about our theories, then being wrong is not shameful. It's expected. Wrong theories are not failures, they're data. Each mismatch is a clue pointing toward a better understanding if you're willing to listen, but listening requires discipline. It requires the courage to say, this doesn't work, to let go of ideas you like, to resist the temptation to explain away inconvenient facts. That discipline is the difference between science and belief. Reality is the final referee. It doesn't applaud cleverness. It doesn't respect intention. It only responds to cause and effect. Align with it and your ideas survive. Ignore it and they collapse. Eventually, always. Our theories are maps. Reality is the territory. Confuse the two and you get lost.
Push two magnets together. Feel that something invisible is fighting you, pushing back against your fingers. Now, flip one around. Snap. They slam. Together so violently you almost lose a fingertip. What just happened? What invisible thing is out there in the empty air between two pieces of metal? Strong enough to hurt you? You felt this your entire life, and I'm about to tell you something that'll make you question every solid object you've ever touched, because the answer, it's not what you think. And by the end of this, you're going to realize you've never actually touched anything in your entire life. Let me show you how deep this goes, T. But first, we need to talk about a problem, because when you ask why about anything, you're walking into a trap. Here's what I mean. Why is your aunt, Minnie, in the hospital? She slipped on ice and broke her hip. Simple enough, right? But why did she slip? Ice is slippery. Everyone knows that. But why? Is ice slippery? Now it gets interesting. When you stand on ice, the pressure from your weight melts a microscopic layer on top. You're not slipping on ice at all. You're slipping on water. Okay, but why does pressure melt ice? Because water does something bizarre. It expands when it freezes. Almost nothing else does this. So pressure wants to reverse that. Expansion, turning it back to liquid. But hold on, why does water expand when it freezes in the first place? And wait, why did she fall when she slipped? That's gravity. Now you're suddenly talking about planets and the entire structure of the universe. Why does falling hurt? Why did her husband call the hospital? Because he cares about his wife. But does he, though? Not all. Husbands do when they're drunk and angry. See what just happened? Every single answer opened 3 more questions. You could keep asking why until you collapse from exhaustion. You have to stop somewhere or you'll be falling forever. And this is exactly what happens when people ask me to explain magnets. People want me to explain magnets using something they already understand, something familiar. Maybe it's like invisible rubber bands, connecting them, pulling them together. And sure, I could tell you that. You'd be satisfied for about 3 seconds. Then you'd ask, okay, but why do rubber bands pull back? And now I'd have to explain forces between molecules, which are electrical forces, which are the exact same forces I'm trying to explain with the magnets in the first place. I'm running in circles using the mystery to explain the mystery. That's not understanding. That's a con game. Here's the truth. Electrical and magnetic forces are fundamental. They're bedrock, the bottom of the well. We don't explain them in terms of something else. We explain everything else in terms of them. Chemistry, that's electromagnetic. Forces between atoms. Biology built on chemistry, which means it's built on electromagnetism, the chair holding you up right now. Electromagnetic, your entire body not falling apart into a cloud of atoms. Electromagnetic, it's everywhere, it runs everything. But here's where it gets weird. You don't think it's strange that you can't push your hand through a table, do you? You push on it. It pushes back. Totally normal. You've done it 10,000 times. But your hand never actually touches the table. No, I'm serious. The atoms in your hand get close to the atoms in the table, and the electrons start repelling each other. That repulsion, that's what you feel is solid, that sensation you call touching. That's the exact same force as the magnets, identical, the same physics, the same interactions at the atomic level. So why does the table seem obvious and the magnets seem mysterious? Only because you grew up pushing on tables every single day and not pushing magnets together. The table is just as strange. You just stopped wondering about it. And this leads us to something absolutely mind-blowing about how strong these forces really are. Electrical forces aren't just strong, they're monstrously, absurdly, incomprehensibly strong compared to gravity. Electromagnetism is stronger by a factor of about 1 followed by 40. Zeros, I don't even know what to call that number. It's not in my vocabulary. This isn't much stronger. This is so much stronger that it doesn't make sense. So why don't we notice? Because atoms are balanced, positive charges in, the nucleus, negative charges orbiting around the outside, plus and minus, everything neutralizes. The most powerful force in the universe is hiding in plain sight because it cancels itself out. But watch what happens when you create even the tiniest imbalance. Comb your hair on a dry day and hold it near some bits of paper. The paper jumps up. To meet the calm, you rubbed off a few electrons, just a few, maybe a trillionth of the total. But the electromagnetic force is so gigantic that even that microscopic imbalance creates something you can see from across the room. Now imagine what happens when you don't let things cancel out, when you force all those tiny effects to line up and work together. Instead of fighting each other, that's where magnets come in. Magnets are special because of what happens inside. Iron, every electron spins. They all do this. It's a fundamental property. In most materials, those spins point every which way. Complete chaos. North, south, east, west, up, down. They all cancel each other out and you get nothing. But in iron, they line up. All those electrons spinning in the same direction. And when they cooperate like that, when they work together, all those tiny magnetic effects stop canceling, they add up, they amplify. Suddenly, you've got something you can feel from across the room. That's why iron is magnetic and copper isn't. Copper has the same physics, the same electrons, the same forces, but the spins point randomly. In iron, they're an army marching in formation. Think of it like a stadium full of people. If everyone talks at once, you hear nothing but noise. But if everyone chants the same word together, you can hear it miles away. Same voice is completely different effect. But this is where it gets really interesting because we can go deeper. We can ask what's actually happening at the most fundamental level when two magnets pull toward each other. And the answer is going to sound insane. At the most fundamental level, it's about particles being exchanged. Electrons don't just sit there staring at each other. They're constantly throwing things back and forth. Photons, little packets of light. And I don't mean light you can see. These are what we call virtual photons. They exist only during the interaction. You can never catch one and examine it directly. It's there and gone. One electron throws a photon, another electron catches it. And that exchange, that endless game of catch happening trillions of times per second, that's what you experience as the electromagnetic force. It sounds bizarre, right? Two things pushing or pulling each other by throwing invisible stuff back and forth. But that's exactly what's happening every time you feel a magnet push against another magnet. Trillions upon trillions of these virtual photons are being exchanged between the electrons in both pieces of metal. And here's the beautiful thing, everything, and I mean everything, electromagnetic comes from just three simple actions. One, a photon goes from one place to another. Two, an electron goes from one place to another. Three, an electron emits or absorbs a photon. That's it. Three actions. From those three actions, you get all of chemistry, all of light, all of magnetism, all of electricity, radio waves, the colors you see, the fact that your hand stops at the table instead of passing through it, like a ghost, all of it. There are no Gia, RS underneath, no hidden mechanism waiting to be discovered. This is how it really works. But hold on, this changes everything about what we thought we knew. In 1873, a physicist named Maxwell wrote down a set of equations. These equations unified electricity and magnetism into a single phenomenon. They're two faces of the same thing. This was probably the most fundamental transformation in human history because once you understand that electrical and magnetic forces are connected, you can do things. You can make a current and a wire create a magnetic field. You can move a magnet near a wire and create a current back and forth. Electricity and magnetism dancing together. Think about what this means in practice. There's a dam somewhere far away. Waterfalls. Turns a big wheel. That wheel is connected to copper wires spinning near some magnets because the copper moves through the magnetic field. Electrons start flowing through the wire. That flow of electrons travels through thin copper cables stretched across hundreds of miles through your entire city, and at the other end in your house, another piece of copper and iron converts that electron flow back into spinning motion. Your fan turns, your refrigerator hums, your lights glow, all the wheels in the city turn because one wheel at the dam turned, stop that one. Everything stops, started again. Everything starts. And what's doing this? Just copper and iron, nothing else. It's not complicated machinery. It's not some special exotic substance. It's just the fundamental nature of electromagnetism. You move. Magnets here. Electrons flow through copper. Magnets move over, they're far away, connected by nothing but wire. What an absolutely fantastic thing nature is. But the precision with which we understand this, that's where things get truly remarkable. We can calculate how magnetic an electron is, not guess, not estimate, calculate, using just those three simple actions. Photon goes here, electron goes there, electron absorbs, photon. You add up all the different ways these interactions can happen, all the possible paths, and you get a number when you measure what nature actually does with extremely precise instruments. The theory and the experiment match to an extraordinary degree. How extraordinary? The difference between our prediction and what we measure is so small. It's like measuring the distance from Los Angeles to New York and being accurate to less than the thickness of a human hair. That kind of precision doesn't exist anywhere else in science. This is the most accurate prediction humans have ever made about anything. And it comes from understanding the electromagnetic force, the same force you felt as a kid pushing two magnets together so we can describe magnetism with spectacular precision. We can predict exactly what it will do. But can we explain why it exists in terms of something more familiar? No, and that's not because we failed. That's because electromagnetic forces, are the familiar thing that explains everything else. But there's a problem, a mystery at the heart of all this that nobody can solve, appears everywhere. It's run thirds everywhere. It's roughly 137, or if you want to be more precise, it's about Joe. 1097, 56, 93, which is approximately fifth. 37, this number determines how strong the electromagnetic force is, how strongly magnets attract, how much. Electrons repel each other. Everything about electricity and magnetism depends on it, and nobody knows where it comes from. We didn't calculate it from something deeper. We didn't derive it from first principles. It just is that number. If you ask why 137 and not 200 or 50, there's no answer. It's one of the great damn mysteries of physics. Where did this number come from? Did somebody write it down somewhere? And we just haven't found it yet. If that number were very different, magnets would be stronger or weaker. Atoms wouldn't hold together the way they do. Chemistry would change completely. We probably wouldn't exist. The whole universe, including every magnet you've ever touched, depends on this mysterious 137, and we have no idea why. But the history of how we figured even this much out, that's a story of near failure and mathematical desperation. When physicists first tried to calculate the magnetic properties of electrons using quantum theory, they got nonsense, infinity. The equations gave infinity, not a really big number actual. Mathematical infinity, that's not an answer, that's a breakdown. For years, people struggled with this. The math seemed fundamentally broken. Then around 1948, a solution appeared. The idea is this: we never measure a bare electron by itself. What we actually measure is the electron plus all its interactions, all those virtual photons being exchanged constantly. So you start from what you can actually measure in experiments, and the infinities get absorbed into those measured quantities. Everything comes out finite. It's called renormalization. Some physicists think it's suspicious, like we're hiding the problems under a mathematical rug. But the results match experiments to incredible precision, those 10 decimal places we talked about. So maybe that's just how nature is. Maybe asking about the bare electron without its cloud of interactions is like asking what a person looks like without their personality. It's a wrong question, but this leads us to an uncomfortable truth about understanding at the deepest level. Here's something I need to be honest about. The way quantum mechanics works, it's nothing like everyday experience. Your brain evolved to understand rocks and trees and animals, things at human scale, things you can throw and catch. But electrons don't. behave like tiny balls. They don't orbit. The nucleus like miniature planets. People say electrons act like waves. Not exactly like particles. Not exactly like a cloud or fog. No, that's not right. Either. If you want a clear mental picture of what's happening inside a magnet at the atomic level, something you can visualize, something you can see in your mind. I can't give you one. Nobody can. What we have is mathematics. We write equations. We calculate. And predictions match reality with extraordinary accuracy. It's like having a perfect calculator that tells you exactly when and where something will happen. It does the arithmetic flawlessly, gives exact answers, but it has no picture in its head, no visualization, no image. It just calculates. That's where we are with quantum mechanics. We calculate what magnets will do. We're extraordinarily good at it, better than almost anything else in science. But the intuitive picture, the ability to really see what's happening that's beyond us, nature at that scale is genuinely different from anything we evolved to understand. And that brings us back to where we started. You push two magnets together. You feel that force in you. Ask the honest answer. It's electrons exchanging virtual photons. It's electron spins lining up in iron. It's the electromagnetic force that holds your entire body together and runs the whole universe. We can describe it with spectacular precision, accurate to 10 decimal places, but if you want me to, explain it in terms of rubber bands or springs or anything else you are ready. No, I can't, because those things are explained by electromagnetism, not the other way around. Magnetism isn't the mystery that needs explaining. Magnetism is the explanation. Magnetism isn't some strange, isolated phenomenon happening in certain pieces of metal. It's part of the electromagnetic force, one of the four fundamental forces of nature. Every atom in your body is held together by it. Every chemical reaction depends on it. When you see colors, that's electromagnetism. When you touch something, solid, that's electromagnetism. When a compass points north, when a motor spins, it's all the same force, and it emerges from just three simple actions. A photon goes from here to there, an electron goes from here to there, an electron emits or absorbs a photon. Three things, that's it. Chemistry, biology, the structure of matter, it all emerges from these three actions combining in countless ways. There are no gears underneath. There's no deeper mechanism hiding behind it, all waiting to be discovered. Now, does that mean we understand everything? No. That mysterious number, 137, nobody knows where it comes from. We can't picture what electrons actually do at the quantum level. We describe nature with mathematics that works beautifully, but our mental images are always approximations, shadows on the wall. But here's the thing about physics. It's experimental. You don't sit around waiting to understand everything perfectly before you do anything. You learn enough to predict what happens. You test it, and if it works, you use it. That dam with copper, wire-making wheels turn across the entire city. That works because we understand electromagnetism well enough, not perfectly, well enough. When you asked why magnets attract, you wanted an answer in terms of something familiar. Rubber bands, springs, invisible strings, pulling things together. But the answer is that magnetism iced the familiar thing. You just didn't realize it. Every time you've touched anything in your entire life, you've been feeling electromagnetic forces. Every solid object, every surface you've ever leaned against, that's electrons pushing against electrons. You've been swimming in electromagnetism since the day you were born. Magnets just make it obvious. They let you feel at a distance what's usually hidden at microscopic scales. So next time you pick up a magnet and feel that push or pull, don't think of it as mysterious. Think of it as nature being honest with you for once, showing you directly what's usually invisible, the same force that holds your own hand, together acting across the empty space between two pieces of iron. That's what's happening. That's what you're feeling. And the fact that we can describe it, predict it, calculate it. You think the speed of light is just a number? 299792458 ms. Fast, really fast. The fastest thing we know, fine. But why is it the limit? Why? Can't you go faster? What stops you? Most people have never really thought about this. They just accept it. Einstein said so. Speed of light is the cosmic speed limit. That's just how it is. But that's not an answer. That's just repeating words. When you really Ask why nothing can go faster than light. When you dig into what's actually stopping you, you discover something so strange, so fundamentally different from everyday experience that it changes everything you think you know about. Space and time. The speed of light isn't just a speed. It's not just the fastest thing. It's the structure of the universe itself. It's woven into the fabric of space and time in a way that makes going faster literally meaningless. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall, drop something, it falls down. 16 ft the first second to be precise. That's what Galileo measured. Drop a ball, drop a rock, drop anything in 1 second. It falls 16 fort. Now the moon. The moon is going around the earth. It's not falling down. It's staying up there orbiting, going in a circle. But wait, is it falling? Think about it. If the moon were just sitting there in space, not moving, what would happen? It would fall toward the earth. Gravity would pull it in, but the moon is moving. It's moving sideways, tangent to its orbit. And because it's moving sideways while gravity pulls it down, it keeps missing the earth. It falls toward the earth, but keeps missing. That's what an orbit is, continuous falling while moving sideways, fast enough to keep missing. Now, here's where Newton had his brilliant insight. The moon is 240,000 mi from the center of the earth. We're standing on the surface 4,000 mi from the center. So the moon is 60 times farther away than we are. Newton said, what if gravity gets weaker with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker, 3 times as far, n times weaker the square of the distance. If that's true, then at the moon's distance 60 times farther, gravity should be 62 times weaker. That's 3,600 times weaker. Now, on Earth, things fall 16 ft in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet, 3,600. Do the math. 16 fort divided by 3,600. That's about 1/12 of an inch per second squared. Wait, let me say that differently. In 1 second, something at the moon's distance should fall toward Earth by 1/12 of an inch, 3,600, because we're talking about the square of time in the formula. 1/12 of an inch, 3,600 equals 16 fort, exactly what we measure on Earth. Newton calculated how far the moon should fall toward Earth in 1 second if gravity follows an inverse square law, and it matched perfectly. The moon is falling at exactly the rate Newton's law predicts. This was huge. This wasn't just a theory. This was a prediction. Newton took a completely independent fact, how fast things fall on Earth, and connected it to another completely independent fact, the period of the moon's orbit and its distance from Earth. Two things that seemed totally unrelated suddenly became connected by one law, the law of gravitation. There was no going back. Now, Newton went further. He calculated what the shape of planetary orbit should be if gravity follows an inverse square law, and he found that it should be an ellipse. And guess what? Planets do move in ellipses. Kepler had already measured that, but Kepler didn't know why. Newton explained it. He got 3 for 2, as it were, and then more things fell into place. The tides. Why are there tides? Because the moon pulls on the Earth. But wait, if the moon just pulls the Earth toward it, there should only be one high tide per day, right? The bulge of water on the side facing the moon. But there are 2 tides per day every 12 hours, roughly. Why? Some people thought the Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both were sort of. Right, but neither got it completely. Newton realized what was really going on. The force of the moon on the Earth and on the water is the same at the same distance. But the water on the near side is closer to the moon than the Earth is, so it gets pulled more. And the water on the far side is farther from the moon than the Earth is, so it gets pulled less. So you get 2 bulges, one where the water is pulled more toward the moon, one where the water is left behind, because the Earth is pulled more than that water. 2 tides per day. Actually, the Earth does the same trick as the moon. It goes around a circle. The center of the circle is somewhere inside the Earth. The Earth and moon both orbit their common center of mass. If you wish, this water is thrown off by a centrifugal force more than the Earth is. And this water is attracted more than the average of the Earth. At any rate, the tides were explained, and the fact that there were 2 a day. A lot of other things became quite clear. Why the Earth is round? Because everything gets pulled in. Why it isn't perfectly round? Because it's spinning. So the outside gets thrown out a little bit and it balances. Why the sun and moon are round, and so on. Now, as science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent. The first. Careful tests involved the moons of Jupiter. By careful observations of the way they went around over a long period of time, one could check very carefully that everything was according to Newton's laws, and it turned out not to be the case. The moons of Jupiter appeared to get sometimes 8 minutes ahead of schedule and sometimes 8 minutes behind the schedule, where schedule is the calculated values according to Newton's laws. 8 minutes, that's a huge discrepancy. Something was wrong. But wait, it was noticed that they were ahead of schedule when Jupiter was close to the Earth and behind schedule when Jupiter was far away. Rather odd circumstance. Mr. Roma, having confidence in the law of gravitation, came to an interesting conclusion. It takes light some time to travel from the moons to the Earth. And what we're looking at when we see the moons are not how they are now, but how they were some time ago. The time it took the light to get here. When Jupiter is near us, it takes less time for the light to come. When Jupiter is farther, it takes longer. So he had to correct the observations for the differences in time, and by the fact that they were this much too early or that much too late, he was able to determine the velocity of light. This was the first demonstration. That light was not instantaneously propagated. Think about what just happened. We found the speed of light, not by measuring light directly, but by having confidence in the law of gravitation when something didn't match, instead of throwing out Newton's law. Roma said, what if light takes time to travel? And he was right. I bring this particular matter to your attention because it illustrates something. When a law is right, it can be used to find another one by having confidence in this law. If something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light, because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery. And this beginning, it's the beginning of that avalanche which has gone on now for 400 years in a continuous process. And we're still avalanching along at high speed at this time. But here's the thing. Once you know the speed of light, once you measure it, you start noticing something very, very strange. Light always travels at the same speed. Always. No matter who measures it, no matter how fast you're moving. Let me make this concrete. You're standing still. You shine a flashlight. You measure the speed of the light coming out. 299.792.458 M's fine. Now you get on a train, a fast train moving at, say, half the speed of light. You shine the flashlight forward. In the direction the train is moving, common sense says the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward from a moving train, the ball moves faster than if you threw it while standing still. But that's not what happens. You measure the light, it's still traveling at 299.792.458 ms, exactly the same speed. You say, okay, maybe I measured wrong. So you get the train going even faster, 90 the speed of light. You shine the flashlight forward again, you measure still 299.792.458 ms. You get frustrated. You get the train going at 99.9999 the speed of light. You shine the flashlight, you measure, still the same speed. The speed of light does not add, it doesn't combine with your speed. It's always the same, no matter how fast you're moving. This should break your brain. This is not how speeds work in everyday life. Speeds add. If you're on a train moving at 50 miles per hour and you walk forward at 3 miles per hour, moving at 53 miles per relative to the ground. But light doesn't do this. Light always moves at the same speed relative to you, no matter how fast you are moving. Why? Einstein realized what was going on. And it's so strange, so contrary to common sense that even now, over a century later, people struggle to accept it. Time and space are not fixed. They're flexible. They bend and stretch to keep the speed of light constant. When you move faster, time slows down. For you, your clock literally ticks slower and distances contract. The space in front of you gets compressed These effects are real, they are not. Optical illusions, they're not. Measurement errors. Time actually slows, space actually contracts. And the amount they change is exactly the right amount to make the speed of light come out the same for everyone. Let me say that again. The universe adjusts time and space, bends them, stretches them, compresses them to ensure that light always travels at the same speed for everyone. The speed of light is not just a speed, it's a structural constant of the universe. Space and time are arranged in such a way that this speed is the same for everyone. Now, here's where it gets even stranger. If you try to accelerate something, anything to the speed of light, something very weird happens. The closer you get to the speed of light, the harder it becomes to go faster. It's not that you run out of fuel. It's not that your engine isn't strong enough. It's that the object itself resists acceleration more and more. We call this relativistic mass increase. As you go faster, your inertia increases. It becomes harder and harder to push you faster. And as you approach the speed of light, your inertia approaches infinity. To actually reach the speed of light, you would need infinite energy, which is impossible. So nothing with mass can ever reach the speed of light, not because of some arbitrary rule, not because of engineering limitations, but because the structure of space-time itself prevents. Light can travel at that speed because photons have no mass. Zero massless particles can travel at the speed of light. In fact, they must. They have no choice. They're always moving at that speed. But anything with mass, it can get close, very close. 99.99999 of the speed of light, but never quite there. Universe won't let you. Now, you might ask, but why? Why is the universe set up this way? Why is there a speed limit at all? And here's the answer that's going to frustrate you. There isn't a deeper why. The speed of light isn't the speed limit imposed on the universe. It's a consequence of how the universe is. Structured space and time are not separate. They're woven together into space-time, and space-time has a geometry, a structure, and that structure has a built-in conversion factor between space and time. That conversion factor is the speed of light. It's not that light is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light happens to travel at that rate because light has no mass, but the rate itself is a property of space-time, not of light. If light didn't exist, the speed limit would still be there. It's a feature of the universe itself. Here's another way to think about. In everyday life, you think of space and time as separate things. You move through space. Time passes. They're independent, but they're not. You're always moving through space-time at a constant rate. Always, but that motion is divided between space and time. If you're sitting still, all your motion is through time. You're moving into the future at maximum speed, 1 second per second. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time. And there's a maximum. If you could move through space at the speed of light, you would have zero motion left for time. Time would stop for you. This is why light doesn't experience time. From a photon's perspective, it's emitted and absorbed in the same instant. No time passes. The universe is frozen. You can't go faster than light because you can't have less than zero motion through time. That's the limit. That's the wall. And here's the beautiful part. This isn't just theoretical. We've tested this over and over and over. Particles and accelerators get accelerated to 99.99999, the speed of light. And guess what? The closer they get, the harder it becomes to accelerate them further, exactly as predicted. GPS satellites have to account for time dilation. They are moving fast and they're in a weaker gravitational field, so time passes differently for them than for us on the ground. If we didn't correct for this, GPS would be off by miles within a day. Muons created in the upper atmosphere by cosmic rays should decay before reaching the ground. Their lifetime is too short, but they're moving close to the speed of light, so time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than should, exactly as relativity predicts. It's not speculation. It's measured. The speed of light being a limit is as well tested as anything in physics. So let's bring this all together. Why is the speed of light the limit? Because space-time is structured in a way that has a maximum rate of cause and effect. That rate is the speed of light. Not because light is special, but because space-time itself has this built-in conversion factor between space and time. You can't go faster because going faster would require moving backwards in time, which doesn't make sense. You can't have negative time. You can't undo cause and effect. The speed of light is the speed at which now propagates through the universe. It's the speed at which information can travel. It's the speed at which forces act. It's the maximum rate of change. And this process, this avalanche of discovery started with Newton figuring out gravity by watching the moon. Then Roma figuring out the SPE, ed of light by watching Jupiter's moons. Then Einstein, realizing that the speed of light is constant and deriving relativity from that. Then thousands of experiments confirming it. Each discovery building on the last, each new insight opening doors to more insights. That's how science works. That's the avalanche that's been going on for 400 years. And we're still avalanching along at high speed at this time. The speed of light isn't just a number. It's the key. It's the thing that unlocks how space and time work. It's, you said, a strange thing happens when you take a scorpion into the dark and shine ultraviolet light on it. It glows brightly, almost theatrically. Now, the first mistake people make is assuming that because something looks dramatic, it must be meaningful. Nature does not work for our entertainment. If you start there, you're already thinking wrong. So let's slow down and ask a better question. Not why does it glow, but what does glow even mean? This is not bioluminescence. The scorpion is not producing light. Nothing inside it is on. What you're seeing is fluorescence. That means energy comes in and energy goes out, changed. Ultraviolet light hits the scorpion's outer shell. That light carries more energy than visible light. The molecules in the scorpion's cuticle absorb that energy, get excited briefly, and then release it at a lower energy level. Lower energy means longer wavelength. Longer wavelength means visible light. No mystery so far. Just physics behaving honestly. Now here's the interesting part. Why does the shell have those molecules at all? The outer layer of a scorpion's body contains certain chemical compounds, byproducts of how its exoskeleton hardens. These compounds just happen to fluoresce under UV light. That's it. No glowing gene, no flashlight function, just chemistry doing what chemistry does. But surely, someone says, it must be useful. Must it? That assumption that every trait has a purpose is one of the laziest habits of the human mind. Sometimes nature keeps things not because they're useful, but because they're not harmful enough to remove. That said, people have proposed ideas. Maybe the glow helps scorpions detect UV light at night. Maybe it provides camouflage under moonlight. Maybe it's a side effect with no function at all. The honest answer is, we don't know, and that's not a failure. That's the frontier. What matters is not pretending certainty, but understanding the mechanism. Once you see the mechanism clearly, the superstition collapses. No mysticism, no exaggerated storytelling. Just energy, molecules, and light. And here's the lesson hiding inside the scorpion. Reality doesn't care about how clever your explanation sounds. It only cares whether it survives contact with evidence. If you see something strange, don't decorate it with meaning. Take it apart, ask what goes in, ask what comes out, and admit ignorance where it remains. That habit, more than any glowing animal, is what actually lights up the dark. You walk into the desert at night, everything is dead quiet, no movement, no sound. Then you flip on an ultraviolet light and suddenly the ground answers back. Bright, electric, alive scorpions are glowing like they've been painted by something that doesn't belong to this world. That moment messes with your head because glowing things are supposed to be special. Fireflies glow for a reason. Deep-sea creatures glow for a reason. So the mind jumps to the same lazy conclusion, this must be important. But the universe doesn't care what we expect, and it certainly doesn't care what feels meaningful. So before we ask why scorpions glow, we need to rescue the question from bad thinking. First mistake, assuming the scorpion is doing something. It's not. The scorpion isn't producing light. It isn't trying to communicate. It isn't signaling danger or beauty or mystery. The scorpion could be completely dead, and it would still glow under ultraviolet light. That single fact should already make you suspicious of every dramatic explanation you've heard. What's happening is not magic. It's not even biology in the romantic sense. It's physics being boring and precise. Ultraviolet light carries more energy than the light your eyes can see. When that high energy light hits the scorpion's outer shell, certain molecules absorb it. For a tiny fraction of a second, those molecules get excited. Then they relax. And when they relax, they give the energy back, but at a lower level. Lower energy means longer wavelength. Longer wavelength means visible light. That glow you see, it's wasted energy leaking out in a form your eyes can detect. The scorpion isn't glowing because it's glowing because the universe doesn't offer refunds. Now let's get uncomfortable, because this is where people start inventing stories. Someone says maybe it helps scorpions find each other. Another says maybe it protects them from predators. Another says maybe it's camouflage under moonlight. All very clever, all very neat, all mostly unsupported. Here's the problem. Nature is under no obligation to be efficient or poetic. If a chemical trait doesn't actively harm survival, it can persist for millions of years without serving a single purpose you'd call meaningful. The scorpion's outer shell, the cuticle, contains compounds created during the hardening process of its exoskeleton. These compounds fluoresce, not because evolution selected them to fluoresce, but because that's simply how those molecules behave when hit with ultraviolet radiation. You don't need intention, you don't need design, you don't need a story. You need molecules and energy. That's enough. Now, could the glow still have a function? Possibly. Some experiments suggest scorpions might use UV sensitivity to judge light conditions. Others suggest the glow might slightly alter how predators perceive them. But notice the language: might, suggest. Possibly, that's honesty. And honesty is rare, because humans hate uncertainty more than they hate being wrong. We want answers that feel complete. We want explanations that sound smart at dinner parties. So we overfit reality. We decorate ignorance with confidence and call it understanding. But real understanding is quieter. Real understanding says, this is what we know, this is how it works, and this is where our knowledge stops. The glow of a scorpion isn't impressive because it's mysterious. It's impressive because it reminds us how easily we fool ourselves into thinking everything has a reason crafted for us to admire. The universe doesn't explain itself. It behaves. Your job, if you're serious about thinking, is not to ask questions that flatter your imagination, but questions that survive contact with evidence. So the next time you see something strange, something glowing in the dark, don't rush to meaning. Don't rush to symbolism. Don't rush to purpose. Slow down. Ask what goes in. Ask what comes out. Follow the energy. Because the real light isn't coming from the scorpion. It comes on the moment you stop believing explanations just because they sound good. If your first reaction is, this must be special, stop right there. That instinct to turn a strange observation into a magical story is the fastest way to stop thinking. The universe doesn't reward awe, it rewards precision. And the moment you assume mystery implies meaning, you've already stepped off the path to understanding. Scorpions glowing in the dark feel like a message. They look intentional, purposeful, almost theatrical, and that's exactly why your brain betrays you. Humans are pattern-hungry machines. We see light where there is darkness and immediately invent a reason worthy of the drama. But nature is not a storyteller. It doesn't care what feels impressive. It only follows rules. So let's demolish the fantasy before it gets comfortable. The scorpion is not doing anything. It is not producing light. It is not sending signals. It is not aware of the glow. You could take a scorpion that's been dead for weeks, shine ultraviolet light on it, and it would glow just as brightly. That single fact should kill every mystical explanation instantly. If death doesn't turn it off, then whatever is happening has nothing to do with intention, communication, or behavior. What you are seeing is not biology trying to impress you. It's physics refusing to cooperate with your expectations. Ultraviolet light carries more energy than visible light. When that high energy light hits certain molecules in the scorpion's outer shell, those molecules absorb the energy. They don't keep it. They can't. They briefly get excited and then relax. And when they relax, they release the energy at a lower level. Lower energy means longer wavelength. Longer wavelength means visible light. That's it. No secret function, no evolutionary trick revealed by moonlight, just energy coming in one form and leaving in another because the laws of nature allow no alternative. Now here's where magical thinking fights back. People say everything in nature exists for a reason. That sentence sounds intelligent. It feels satisfying. It is also dangerously sloppy. Nature doesn't design with intention. It filters. Traits that kill organisms disappear. Traits that don't stay, whether they're useful, neutral, or just along for the ride. The chemicals in a scorpion's cuticle exist because they help form a tough outer shell. Their ability to fluoresce is a side effect. Not a goal, not a feature, a consequence. The glow is not an answer. It's a leftover, but surely someone insists it must do something. Maybe, maybe not, and here's the uncomfortable truth. Ignorance doesn't vanish just because you demand meaning. If there is a function, it has to be demonstrated, not imagined. You don't get to promote a hypothesis just because it feels elegant. Evidence doesn't care about elegance. Some experiments suggest scorpions might sense ultraviolet light indirectly. Others speculate the glow could affect how predators see them. These are ideas, not conclusions. And pretending otherwise is not curiosity, it's decoration. The honest position is this: we understand the mechanism, but the purpose, if any, remains uncertain. And that should not bother you. It should excite you. Because the moment you stop insisting that everything must make sense in human terms, you begin to see reality as it is, not as a story built for your comfort. The glow stops being magical and becomes more interesting. It becomes a reminder that the universe operates without consulting our intuition. This is the deeper lesson hiding under the scorpion. Magical thinking feels good because it closes the question. Real thinking keeps it open. It tolerates not knowing. It resists the urge to fill gaps with confidence just to feel smart. When you reject magical explanations, you don't lose wonder. You trade cheap wonder for durable awe, the kind that survives scrutiny, the kind that doesn't collapse the moment someone asks, "How do you know?" So the next time something glows in the dark, don't ask what it means, ask what it's made of. Ask what energy is doing. Ask what assumptions you're sneaking in without noticing, because the universe is not mysterious in the way fairy tales are mysterious. It is mysterious in the way a lock is mysterious, until you understand the mechanism, and once you do, the glow doesn't disappear, only the nonsense does. If you can't define what you're looking at, you have no business explaining it. Before meaning, before theory, before imagination runs wild, there is a simpler obligation: say exactly what is happening and say it cleanly. Most confusion survives only because we tolerate sloppy words. So let's be precise. When people say a scorpion glows in the dark, they're already lying to themselves, just a little, but enough to cause trouble. The scorpion does not glow in the dark. In complete darkness, it is invisible. Nothing happens, no light appears. The glow requires something else first. Without that condition, there is no phenomenon at all. The scorpion glows only when ultraviolet light strikes it. That distinction matters more than it sounds, because the moment you skip it, you invite fantasy. Glowing things that produce their own light suggest life, intention, activity. But this is not that kind of glow. This is not fire, not electricity, not chemistry generating energy from within. This is fluorescence. Fluorescence means energy comes in from the outside, is temporarily absorbed, and then released in a different form. Nothing is created. Nothing is powered. The system is passive. The object is not acting. It is reacting. Ultraviolet light carries more energy than visible light. When that high-energy radiation hits certain molecules in the scorpion's outer shell, those molecules absorb the energy. For a brief moment, their internal structure is disturbed. Then physics does what physics always does. It settles things back down. The energy is released, but at a lower level. Lower energy corresponds to longer wavelength, and longer wavelength is what your eyes can see. So the glow is simply visible light leaking out as the system relaxes. That's the phenomenon. No more, no less. If you replace that definition with something vaguer, the scorpion lights up or it emits light, you've already sabotaged your understanding, because those phrases smuggle an action where none exists. They make it sound alive in a way that has nothing to do with life. A dead scorpion fluoresces, a crushed scorpion fluoresces, a shed scorpion exoskeleton fluoresces. That alone should force you to tighten your language. What fluoresces is not the scorpion as a creature, but the chemical structure of its cuticle. The outer shell contains compounds formed during the hardening process, byproducts of molecular bonds locking into place. These compounds have electronic structures that respond to ultraviolet radiation in a very specific way. That response is not optional. Given the same molecules and the same energy input, the same output will occur every time. There is no decision involved. No adaptation happening in the moment. No behavior being expressed. Just physics repeating itself faithfully. This is why definition matters. Once you define the phenomenon accurately, entire categories of explanation disappear automatically. You no longer ask whether the scorpion uses the glow to communicate, because nothing is being generated. You no longer wonder how the scorpion turns it on, because there is no switch. You stop asking biological questions about something that is fundamentally physical. And this is where most people go wrong, not because they lack intelligence, but because they rush. They want the satisfying answer before earning the correct question. So they explain a mirage instead of the optics that produce it. Precision is not pedantic. Precision is merciful. It saves you from wasting years chasing ideas that were wrong at the sentence level. Once you understand what fluorescence actually is, the glow loses its supernatural flavor. It becomes ordinary in the best possible way. The same effect appears in minerals, plastics, paper, even laundry detergent. The scorpion is not unique because it fluoresces. It's only striking because you didn't expect it to, and that surprise says more about your expectations than about the scorpion. The real intellectual discipline is learning to stop exactly where the facts stop, to resist adding drama, to resist upgrading a description into a story. When you define the phenomenon precisely, you don't shrink the mystery. You relocate it to the correct place, not in the glow itself, but in the deeper question of why certain molecules exist at all, why matter behaves the way it does, and why the universe is intelligible enough for us to notice. But you don't get there by skipping steps. You start by saying, without exaggeration and without poetry, energy goes in, energy comes out, and light is just the receipt. Everything else must earn its place after that. Forget the animal for a moment. Forget desert stingers, danger, and fear. If you want to understand what's happening, you have to be ruthless enough to remove everything that doesn't matter. When you do that, what's left is not biology, not mystery, not intention. What's left is physics, plain, stubborn, and unimpressed by how strange the result looks to you. At the most basic level, this is a story about energy, nothing more. Energy arrives, energy leaves, and the form it takes in between is dictated by rules that do not care what object is involved. A scorpion just happens to be in the way. Ultraviolet light is electromagnetic radiation with shorter wavelengths and higher energy than visible light. When that radiation strikes matter, one of two things happens. It passes through or it is absorbed. In the scorpion's outer shell, some of that ultraviolet energy is absorbed by electrons bound within certain molecules. Now, here is the critical point that people miss. Electrons do not absorb energy politely. They jump. They move from one allowed energy state to another. These states are not continuous. They are quantized. There are only certain places an electron is allowed to be. When ultraviolet light provides just the right amount of energy, an electron jumps to a higher state. But nature does not like instability. That excited state cannot last. The electron must fall back down. And when it does, the energy difference has to go somewhere. It leaves as a photon. That photon has less energy than the one that came in. Why? Because some of the incoming energy is lost to tiny vibrations, heat, and internal rearrangements. Energy is conserved but not preserved in the same form. High energy ultraviolet goes in. Lower energy visible light comes out. That is fluorescence. No intention, no benefit. Just bookkeeping. If this sounds underwhelming, good. Underwhelming explanations are usually the correct ones. The scorpion's glow is not special because of the scorpion. It is special because your intuition expects light to mean activity. But physics doesn't share that intuition. To physics, light is just energy moving through space, interacting with charged particles. The molecules in the scorpion's cuticle have electronic structures that make these energy transitions likely. That's not a biological decision. It's a consequence of how atoms bond, how electrons arrange themselves, and how electromagnetic fields interact with charge. Change the molecules, the glow disappears. Change the light source, the glow disappears. Nothing else needs to change. This is why a dead scorpion fluoresces. This is why a shed exoskeleton fluoresces. The living system is irrelevant once the structure is in place. The physics does not check for a heartbeat. And here's the uncomfortable lesson hidden in all of this. Once you strip the problem down far enough, many why questions dissolve. They were never about causes, they were about discomfort. We ask why when we really mean this feels surprising. But physics is not surprise. The same principles apply whether the object is a scorpion, a rock, or a highlighter pen. The universe runs on constraints, not intentions. It allows certain energy transitions and forbids others. When conditions line up, light appears. When they don't, it doesn't. That's it. No secret signal. No evolutionary conspiracy. No hidden message glowing for predators or prey. If a function exists, it must sit on top of this mechanism. It cannot replace it. And if no function exists, the mechanism stands perfectly well on its own. Understanding this requires discipline because it means letting go of the satisfying story in favor of the dull truth. But the dull truth has a strange power. It works everywhere, every time. Once you see the physics clearly, the glow stops being mystical and becomes inevitable. Of course it glows. Given those molecules and that energy, how could it not? And that realization is far more valuable than the glow itself, because it teaches you how to think when something looks extraordinary. You don't ask what it means, you ask what laws are being obeyed. Strip it down far enough, and the universe always answers in the same language. Let's make one thing clear before we start. Ultraviolet light is not mysterious, and it is not special just because you can't see it. The only reason it feels strange is because your eyes stopped where nature didn't. Reality does not end at human vision, and it doesn't slow down to explain itself. Light is energy that travels in waves. Some waves are long, some are short. Long waves carry less energy. Short waves carry more. Your eyes are tuned by accident, not by design, to a very narrow slice of that spectrum. That slice is what you call visible light. Everything else existed long before your eyes learned to notice anything at all. Ultraviolet light is just light with waves shorter than violet. That's it. No drama required. Because the waves are shorter, the energy they carry is higher. That higher energy is the entire story. Ultraviolet doesn't glow, burn, or excite things because it wants to. It does so because energy, when concentrated, forces matter to respond. Think of it like throwing balls at a door. A slow, soft throw barely moves it. A faster throw makes it shake. Throw hard enough, and something happens. Not because the door understands intention, but because energy crossed a threshold. Ultraviolet light crosses thresholds that visible light usually doesn't. When UV light hits matter, it can disturb electrons inside atoms and molecules. Not destroy them, just push them into higher energy arrangements. That push is temporary. Electrons don't stay excited, they relax. And when they do, the extra energy has to go somewhere. Sometimes it becomes heat. Sometimes it becomes chemical change. And sometimes, when the structure allows, it becomes light you can see. That's why ultraviolet light is so useful for revealing things that otherwise stay hidden. It doesn't add anything new. It exposes behaviors already built into matter. Now here's the part people misunderstand. Ultraviolet light is not dangerous because it is evil or harsh. It's dangerous in some cases because it carries more energy per wave. Enough energy, delivered often enough, can break chemical bonds. That's why too much UV damages skin. Not because the light is malicious, but because physics does not negotiate. The same rule explains fluorescence. When ultraviolet light strikes certain molecules, it delivers more energy than they can quietly absorb. The electrons jump. The structure momentarily rearranges. Then the system relaxes and excess energy escapes as visible light. You see a glow, but what you're really seeing is matter failing to hold on to energy it didn't ask for. The scorpion doesn't glow under ordinary light because ordinary light doesn't push the molecules hard enough. The electrons stay where they are. Nothing interesting happens under ultraviolet. They get kicked upstairs and have to find their way back down. That's all ultraviolet is doing, pushing harder. And this is why teaching it to a smart child works better than teaching it to an overconfident adult. A child doesn't insist that invisible things must be unreal. A child is comfortable with the idea that eyes are limited. Adults, on the other hand, often confuse familiarity with truth. Ultraviolet light doesn't exist to surprise you. It exists because electromagnetic waves can have many wavelengths, and the universe didn't consult your senses when it picked them. Once you understand that, the glow stops being impressive and starts being predictable. Of course, high-energy light can force certain molecules to respond differently. Why wouldn't it? The rules are consistent. The surprise was never in the light, it was in your assumptions. So when ultraviolet light makes a scorpion shine, it's not revealing a secret message or hidden power, it's revealing your blind spot. It's showing you that reality is richer than what your eyes report and simpler than the stories you invent to explain what you didn't expect. Teach that to a child and they'll nod. Tell it to an adult wrapped in certainty and they'll argue, physics doesn't care either way. You want the real reason, you have to go small, smaller than animals, smaller than organs, smaller than cells. The glow doesn't belong to the scorpion as a creature. It doesn't even belong to life. It belongs to molecules that would behave the same way whether the scorpion ever existed or not. The moment you stop at the scorpion glows, you've already missed the explanation. What actually fluoresces is the scorpion's cuticle, the hard outer shell that protects its body. That shell is built mostly from chitin, layered and hardened through a chemical process that locks molecules into rigid structures. During that process, certain compounds are formed, complex organic molecules with very specific electronic arrangements. These arrangements are the entire story. Electrons in molecules don't roam freely. They sit in well-defined energy levels, like rungs on a ladder. They can't stand between rungs, and they can't move unless energy forces them to. Ultraviolet light carries exactly the kind of energy that can kick these electrons upward to a higher rung. When UV light hits the scorpion's cuticle, some of that energy is absorbed by molecules such as beta-carbolines and related compounds embedded in the hardened shell. These molecules are not there to glow. They are there because chemistry, when left alone, produces them as byproducts of structural stability. The glow is collateral damage. Once an electron absorbs ultraviolet energy, it jumps into an excited state. But that state is unstable. Nature does not tolerate excess energy hanging around. The electron must fall back down to its original state. When it does, the energy difference has to be released. Here's the crucial detail. It does not come out the same way it went in. Some of the absorbed energy is lost internally, converted into tiny vibrations of the molecule, into heat you'll never notice. What remains is released as a photon of lower energy. Lower energy means longer wavelength. Longer wavelength means visible light. That visible light is the glow. Nothing is created. Nothing is activated. The molecule is simply obeying the only transitions it's allowed to make. If those molecules didn't exist, there would be no fluorescence. If the electrons had different energy gaps, the color would change. If ultraviolet light weren't present, nothing would happen at all. This is why the glow color is consistent. This is why it doesn't flicker with mood or behavior. This is why a shed exoskeleton glows just as brightly as a living scorpion. The phenomenon lives entirely at the molecular level, where life and death are irrelevant distinctions. People desperately want this to be more romantic than it is. They want to believe evolution designed a glowing warning system or a secret communication channel. But evolution doesn't design at the molecular scale with foresight. It filters outcomes. If a molecule strengthens a shell, it stays. If its side effects don't kill the organism, they are tolerated. Fluorescence is not selected for. It's simply not selected against. The glow is not a feature. It's a consequence, and this is the part that's hard to accept. If you removed every scorpion from the planet but left behind those same molecules arranged the same way, the physics would still work. The electrons would still jump. The energy would still be released. The light would still appear. The explanation does not care about animals. This is why does it glow is a misleading question. It implies intention. A better question is, what molecular structure allows this energy transition? That question has a real answer, grounded in chemistry and quantum mechanics, not storytelling. Once you see that, the mystery collapses in the best possible way. Not into disappointment, but into clarity. The glow stops being a signal and becomes a demonstration, a visible reminder that matter has rules, and those rules operate whether you're watching or not. The scorpion doesn't glow to tell you anything. The molecules glow because they have no choice. And if that feels less magical, good. Because the real wonder isn't that animals glow under ultraviolet light. The real wonder is that invisible rules written into the structure of matter itself are so consistent that you can shine light on them and watch them obey. That's not poetry, that's reality working exactly as advertised. The most dangerous sentence in science sounds harmless. It must have evolved for a reason. That line has killed more thinking than ignorance ever did. It feels responsible, it feels respectful to nature, and it is usually wrong. Here's the mistake hiding inside it, the assumption that evolution is a designer. It isn't. Evolution does not plan, does not aim, does not care whether something is clever, beautiful, or meaningful to you. It does not ask what a trait is for. It only asks one brutal question: does this kill you before you reproduce? If the answer is no, the trait is allowed to stay. That's the whole system. So when people see a scorpion glowing under ultraviolet light and immediately ask, what advantage does that give it? They've already smuggled intention into a process that has none. They are treating evolution like an engineer instead of what it really is, a filter that throws away failures and keeps everything else by default. This is why weak evolutionary explanations are so tempting. They sound scientific without requiring discipline. You just invent a story that feels plausible and call it adaptation. Predator deterrence, communication, camouflage, pick your favorite. The problem is not that these ideas are imaginative, it's that imagination is cheap. Evidence is not. A real evolutionary explanation has to survive a simple test. Remove the supposed function and ask whether the organism would actually suffer. If the scorpion stopped fluorescing tomorrow, would it die faster? Would it fail to hunt? Would it fail to mate? There is no serious evidence that it would, and that should bother you because it means the glow may not be an adaptation at all. It may be what biologists call a byproduct, a side effect of something else that is useful. The scorpion needs a hard, durable exoskeleton. The chemistry that creates that shell happens to produce molecules that fluoresce under ultraviolet light. The glow comes along for the ride. That's not a flaw in evolution. That's how evolution mostly works. Nature is full of accidents that stuck around simply because they didn't cause enough trouble to be removed. Evolution doesn't polish every detail. It tolerates mess. It keeps quirks. It leaves fingerprints of history all over living things. Expecting every trait to have a clean, optimized purpose is like expecting every scar on your body to be fashionable. People resist this idea because it feels unsatisfying. They want nature to be elegant. They want every detail to justify its existence. But reality is under no obligation to meet aesthetic standards. Here's the deeper problem. When you assume every trait must have a function, you stop asking good questions. You stop investigating mechanisms and start collecting stories. You confuse explanation with narrative closure. The glow feels meaningful, so you give it meaning. But feeling is not evidence. A strong scientific mindset does the opposite. It assumes nothing is special until proven otherwise. It demands measurements. It tolerates uncertainty. It accepts that we don't know is not a failure but an honest checkpoint. Could the fluorescence have some secondary use? Possibly. But possibility is not proof. Until you can show that scorpions without this glow are at a disadvantage compared to those with it, the safest assumption is that the glow is incidental, and that assumption is not pessimistic. It's discipline. This is where many people get uncomfortable, because it forces them to abandon a comforting belief that nature is always cleverer than we are. Sometimes it is. Often it isn't. Sometimes it's just good enough. Evolution does not produce perfection. It produces survivors. The glow survives because it doesn't interfere with survival. That may be the entire explanation. Once you accept that, something interesting happens. The scorpion stops being a symbol and becomes a case study in intellectual hygiene. It teaches you how easily humans project intention onto systems that operate without it, how quickly we turn description into purpose, how badly we want the universe to be a story written for us to admire. Destroying weak evolutionary assumptions isn't about being cynical. It's about respecting the process enough not to lie about how it works. Nature does not owe you meaning. Traits do not owe you functions. And glowing does not owe you a reason if you want real understanding. You have to be willing to let go of beautiful explanations when the evidence doesn't support them. Because the moment you stop demanding that everything makes sense in human terms, you finally start seeing evolution clearly, not as a wise designer, but as an indifferent editor, crossing out only what fails. And that, whether you like it or not, is far more powerful than any glowing myth. The honest answer is uncomfortable, which is exactly why people avoid it. When you ask what the scorpion's glow is for, the most truthful response is not a confident explanation. It's a list of competing ideas, none of them fully proven, all of them constrained by the same physical facts. Anything cleaner than that is not understanding. It's marketing. So let's do this properly, without pretending certainty where it doesn't exist. One idea is that the glow helps scorpions sense light. Scorpions are nocturnal. They avoid bright conditions and prefer darkness. Some researchers suggest that because their entire body fluoresces under ultraviolet light, scorpions might be indirectly sensitive to UV levels in their environment. The logic goes like this. More ambient UV means more fluorescence, which might affect how much light reaches their simple eyes or how their nervous system responds. In theory, this could help them decide where to hide. Notice the words might and could. That's not weakness, that's accuracy. The mechanism is plausible, but the evidence is limited. The glow exists, the behavior exists. The causal link is still under investigation. Another hypothesis is camouflage. Under moonlight, especially in desert environments, ultraviolet light is present. Some argue that fluorescence could break up the scorpion's outline or make it blend into the background in a way predators perceive differently. Again, this sounds clever. And again, the problem is proof. Predators see the world differently than humans. What looks obvious to us under a UV lamp may be irrelevant to an owl, a lizard, or a rodent without controlled experiments showing improved survival due to fluorescence. Camouflage remains an idea, not an explanation. There's also the warning signal hypothesis. Bright colors in nature sometimes signal danger or toxicity. So the thought goes, perhaps glowing makes predators hesitate. But here's the problem. The glow only appears under ultraviolet light, not normal night conditions. A warning sign that requires special lighting is a poor warning sign. Nature tends to be more efficient than that. Then there's the least exciting and most likely possibility. The glow does nothing at all. It's a byproduct, a chemical side effect of building a strong exoskeleton. It persists because it doesn't interfere with survival. Evolution didn't remove it because there was no reason to. People resist this explanation because it feels like giving up. It feels like admitting ignorance. But in science, admitting ignorance is not surrender, it's positioning. It tells you where the edge of knowledge actually is. Here's the rule most people forget. Multiple hypotheses can coexist without one being correct yet. Reality does not rush to meet our desire for closure. Sometimes the correct answer is still buried under insufficient data. Presenting competing hypotheses honestly means doing something humans hate, living without a tidy conclusion. It means saying, here are the ideas, here's what supports them, here's what doesn't. And here's what we still don't know. That's not weakness, that's intellectual strength. The moment someone tells you with confidence that the scorpion glows because of one definitive evolutionary advantage, you should become suspicious. Confidence without proportional evidence is a red flag, not a virtue. Science is not a collection of answers. It's a method for not lying to yourself. And part of that method is resisting the urge to promote speculation into fact just because it sounds reasonable. The glow remains, the physics is clear, the chemistry is understood, and the biological significance is still under debate. That's the honest state of affairs. And that honesty is the point, because the real lesson isn't about scorpions. It's about how knowledge actually works. Progress doesn't come from choosing the most attractive hypothesis. It comes from testing ideas until only one survives. Until then, the glow stands as a reminder. The universe does not care whether your explanation feels complete. It only cares whether it is true. Anything less than that is just storytelling with scientific vocabulary. The most powerful sentence in science is not, "I know," it's, "I don't know yet." And the reason people avoid saying it is the same reason progress depends on it. Ignorance is uncomfortable, but pretending it doesn't exist is fatal to thinking. When it comes to the scorpion's glow, we know a great deal. We understand the physics. We understand the chemistry. We can describe the mechanism in detail, down to energy levels and molecular structures. And then, right where people want the story to end, knowledge stops. The biological purpose, if there is one, remains uncertain. That gap is not a failure. It's fuel. Productive ignorance is not the absence of information. It's the honest recognition of where understanding ends and questions begin. Without that recognition, there is nothing to investigate, only conclusions to defend. This is where weak minds rush to fill the silence. They invent purposes. They promote speculation into certainty. They confuse plausibility with proof. That feels productive because it creates closure. But closure without evidence is intellectual death. It freezes inquiry and replaces curiosity with confidence. Real progress moves in the opposite direction. It opens the gap wider, labels it clearly, and refuses to decorate it. Consider what would happen if scientists simply decided early on that the scorpion's fluorescence must be a warning signal. Papers would be written to support it. Data would be interpreted to fit it. Alternatives would quietly disappear. The glow would be explained, and no one would bother checking whether the explanation was true. Ignorance, honestly acknowledged, prevents that. By admitting we don't yet know the function, researchers stay free to test competing ideas. They can design experiments that isolate variables. They can measure survival, behavior, perception. They can be surprised. And surprise is where discovery lives. The moment you think you already understand something, you stop looking carefully. That's not wisdom. That's blindness wearing confidence. Productive ignorance also teaches discipline. It forces you to separate mechanisms from meanings. Just because you can explain how something happens does not mean you can explain why it exists. Those are different questions. And confusing them leads to shallow explanations that collapse under scrutiny. The scorpion doesn't glow to teach you a lesson, but it accidentally demonstrates one anyway, that understanding grows outward from solid ground, not inward from assumptions. Ignorance is not a void to be filled with noise, it's a boundary, and boundaries are useful. They tell you where to push. Every serious scientific advance begins with a clearly marked ignorance. Gravity worked long before it was understood. Electricity lit rooms before anyone could explain it. DNA carried information before its structure was known. Progress didn't wait for certainty. It grew because people were honest about what they didn't know. And here's the part people miss. Ignorance, when handled correctly, is not passive. It's active. It directs attention. It sharpens questions. It keeps explanations honest. The problem is not ignorance. The problem is fake knowledge. Fake knowledge sounds confident. It's clean. It fits into headlines, it makes people feel smart, and it actively resists correction. Productive ignorance, on the other hand, invites challenge. It expects to be revised. It leaves room for reality to disagree. When you say, "we don't know," you're not giving up authority, you're claiming credibility, you're signaling that you value truth over comfort. The scorpion's glow remains partially unexplained in evolutionary terms, and that's exactly why it's interesting. If everything about it were settled, it would be a fact to memorize, not a question to explore. Ignorance keeps it alive as a subject of inquiry. This is not a weakness of science. It's its engine. So when you encounter a gap in understanding, don't rush to close it. Sit with it. Define it. Protect it from bad explanations. Because once ignorance is properly framed, it becomes the most productive thing in the room. Knowledge grows by respecting what it hasn't earned yet. The most dangerous moment in thinking is the instant you believe you've seen something clearly. Observation feels like truth. It feels solid, but observation by itself is just raw input. What matters and what quietly shapes everything you believe is the habit that kicks in immediately afterward. You see a scorpion glow under ultraviolet light. That's the observation. Everything that follows is optional. Meaning, purpose, explanation, those are not in the glow. They come from you. This is where thinking habits reveal themselves. One habit says, "That's amazing. What does it mean?" Another says, "What exactly am I seeing? Under what conditions? What changes if I remove one variable?" The first habit produces stories. The second produces understanding. Most people don't realize how quickly they jump from observation to interpretation. The glow appears, and within seconds, the mind fills the gap with intention. Warning signal, communication, evolutionary advantage. These ideas feel natural because the brain hates silence. It wants closure. It wants patterns to resolve into meaning. But good thinking is not fast. It is patient. It resists the urge to explain before defining. It treats observation as a starting line, not a finish. The glow teaches this lesson perfectly because it punishes sloppy habits. If you assume the scorpion is doing something, you're wrong. If you assume the glow must disappear with death, you're wrong. If you assume visibility implies purpose, you're wrong. Each assumption collapses the moment you test it. This is why disciplined thinkers develop a reflex. When something looks strange, they first ask what would make it stop. Change the light. Remove the organism. Alter the material. If the phenomenon survives those changes, your interpretation was too human. That habit, asking what doesn't matter, is more powerful than asking what does. The scorpion's glow exists whether anyone is watching. It exists whether the scorpion benefits or not. That forces a mental correction. Maybe not everything you notice is meant for you. Maybe observation is not an invitation to meaning, but a challenge to restraint. Good thinking habits treat surprise as a warning sign. Surprise means expectations were wrong, not that reality is special. When you feel amazed, it's a cue to slow down, not speed up, to check assumptions, to separate what you know from what you're projecting. This habit scales. The same mistake people make with glowing scorpions appears everywhere in statistics, in medicine, in economics, in everyday arguments. We see a pattern and rush to explain it before confirming it exists. We observe correlation and assume cause. We mistake visibility for importance. The glow doesn't teach you biology. It teaches you humility. It shows how easily the mind decorates facts, how effortlessly it upgrades observation into narrative, and how often confidence arrives before evidence. Strong thinking habits reverse that order. Evidence first, mechanism second, meaning last, and only if it survives. There is another habit hidden here, quieter but just as important, comfort with incompleteness. Observing the glow does not require resolving it. You can hold the fact without owning the explanation. That ability to live with unanswered questions without anxiety is a mark of intellectual maturity. People who lack this habit don't actually want understanding, they want certainty. And certainty is the enemy of curiosity. The glow under ultraviolet light is not a lesson because it's rare or exotic. It's a lesson because it's simple and easy to misread. It exposes how much of thinking is automatic and how little of it is examined. The universe presents data. You supply the habits, change the habits, and the same observation leads to deeper understanding. Keep bad habits, and even the clearest phenomenon turns into superstition. So the next time you observe something unexpected, don't ask what it means. Ask what you're assuming. Ask what you're ignoring. Ask how your thinking habits are shaping the conclusion before you even realize you've reached one, because the glow is not the test. Your reaction to it is. Here's the challenge, and it starts uncomfortably close to you. The next time something surprises you, resist the urge to explain it. That impulse to rush toward meaning, to grab the first story that feels satisfying, is not intelligence. It's impatience pretending to be insight. And if you don't learn to catch it, it will quietly sabotage every serious thought you ever have. You've watched a scorpion glow under ultraviolet light. Fine, that's the observation. Now comes the real test. What do you do next? Most people fail right here. They reach for purpose. They ask what it's for. They assume nature owes them a reason shaped like a story. And the moment they accept an answer that feels good, they stop looking. Curiosity dies not from lack of information, but from premature certainty. So here's the challenge. Stop rewarding yourself for explanations that arrive too easily. When you hear an answer, don't ask whether it sounds smart. Ask whether it could be wrong. Ask what evidence would actually change your mind. If you can't think of any, you're not holding knowledge, you're holding a belief. The universe is not obligated to be neat. It does not compress itself into explanations that fit comfortably in your head. If your understanding feels effortless, that should make you suspicious. Real understanding usually costs something: time, discomfort, and the willingness to sit with uncertainty longer than feels polite. Challenge yourself to separate three things you normally blur together: what you saw, what you know, and what you're guessing. What you saw: light appears under ultraviolet radiation. What you know: the physics and chemistry explain how it happens. What you're guessing: why it exists at all. Most people collapse those into one sentence and call it comprehension. Don't. The challenge is to develop the discipline to stop exactly where the evidence stops and not one step further. That restraint is harder than it sounds. It goes against every social reward system you've learned. Confidence gets praised, hesitation gets punished. Saying "I don't know" sounds weak to people who mistake noise for clarity. Ignore them. Train yourself to be dangerous in a different way. Be the person who asks the boring questions that actually matter, the one who slows the conversation down, the one who refuses to upgrade speculation into fact just to keep things moving. Here's a practical test. The next time you hear a confident explanation, ask yourself whether it explains the mechanism or just assigns a role. Mechanisms constrain reality. Roles decorate it. One survives scrutiny. The other collapses the moment conditions change. Another test: imagine the phenomenon stripped of its context. No animal, no drama, just matter and energy. If the explanation still works, you're closer to the truth. If it doesn't, you were relying on narrative, not understanding. This is not about scorpions. The glow is just a training exercise. The real battlefield is everywhere else. News headlines, scientific claims, motivational nonsense, viral facts dressed up as wisdom. The same bad thinking habits apply, and the cost is much higher. Your challenge is to become allergic to fake clarity. When something feels obvious, push harder. When something feels mysterious, slow down. When someone sounds certain, look for what they're not saying. And when you feel the urge to conclude, ask whether the conclusion has actually earned the right to exist. Most people want answers. Very few want the discipline required to deserve them. If you take this challenge seriously, you'll notice something unsettling. The world becomes less magical in the cheap sense, but far more impressive in the real one. Not because you know more, but because you stop lying to yourself about what you don't. So don't walk away impressed by a glowing scorpion. Walk away sharpened. Carry the habit with you. Apply it ruthlessly, because the final test is simple and unforgiving. Can you resist certainty long enough for truth to catch up? If you can't, the glow meant nothing. If you can, you don't need the glow at all.